Last time, we made a lot of progress with two fundamental physical laws, Faraday's law and Lenz's law. And then we used that progress to move us towards the possibility of analyzing circuits which harness this Maxwell's phenomena, which comes in the form of Faraday's law. Now, Faraday's law states that the line integral of E dot dl around a closed loop is not the zero which we would expect, because we had been thinking so far that electric fields were conservative. Rather, there's an additional term that enters in when we are not in steady state, which involves time derivatives, in particular the time derivative of the magnetic flux enclosed by the loop about which we are computing the integral of the electric field. This comes to us with a certain prefactor, which is just a minus sign, but this minus sign is critically important, and it directly reflects Lenz's law, or what I like to call the no free lunch law. This minus sign works in with all of our definitions in such a way that any EMFs that are induced via Faraday's law like this will have a sense of direction always, such that any induced currents that they produce, or potentially induced currents, if there were some charges around for those EMFs to push around, either whether they are actually induced or potentially induced, the currents that they would induce would have such a direction such as to oppose any change in magnetic flux. Because if they were to enhance it, then we would be basically getting our free lunch. And that opposition can come in either or both of two different forms, either mechanically, if we are inducing the EMF by motion, the forces on the resulting currents will be tending to try to resist the motion, or magnetically, where the induced currents will be such as to create additional fields which would oppose, again, that change in the magnetic flux.